Okay. So I'm Beth, and I'll talk about the SCADS, which is our storage system, and the directors, or how we're actually scaling that. And this is work with a bunch of students and our advisors. So where this fits into the big picture is we're looking at the director and as well as the SCADS, the underlying storage layer, and how we're going to actually scale each one of those namespaces within SCADS. So if we look at our canonical three-tier stack, we know that cloud computing provides this opportunity to scale up our number of resources, as well as the incentive to scale down when we want to save money. And large-scale internet applications are particularly well suited to leverage this opportunity for several reasons. One of them being what we talked about is the RAD mission. Enable someone to write an app over the weekend, start really small, and then scale up over time as they get more popular. But additionally, they can leverage it to do dynamic resource allocation in response to periodic or unexpected workload changes. And so while this has been done in kind of the stateless web tier, and what we've also done in the demo today, I'm going to be talking actually about the storage layer underneath. And in particular, so if the internet application is using a scalable storage system, so that means horizontally scalable, so able to actually go across multiple machines, and has some sort of mechanism for doing data movement or an API for data movement between servers, then we can leverage the cloud to do this dynamic resource allocation. But what's challenging for doing scaling in this context is that because we're an interactive web application, we have this notion that we want all the user's experience to be really good. So we specify these service level objectives that are specified in the upper percentiles of response time. So for instance, one example SLO might be over a 1-minute interval, 99% of your requests are satisfied in less than 100 milliseconds. So to motivate why we want to do dynamic scaling, let's look at an example of a workload trace we'd actually like to support. So this is actually from Wikipedia from a couple summers ago, and it just shows the aggregate workload over time. So as you see, it's more or less a diurnal pattern. However, on one of the days, there's a spike, which actually corresponds to when Michael Jackson died. So if we were to say, in our interactive application, so say we have this storage system, and we were actually to partition the data across, say, 10 nodes in this case. Now, when the spike for Michael Jackson hits, it would actually be on one particular server, because where the data item would live, and that spike would actually look more like this. And so if we wanted to support, have enough servers in our cluster to support this kind of spike for any data item that might occur at any time, in this case, we have to over-provision by 300%. So obviously, we don't want that. We want to do some sort of dynamic solution. And that's what I'll be talking about today. So I mentioned, cloud computing is great for scaling up when you need it, and also scaling down to save money on those least resources. And so we're looking at the policy for doing that scaling mechanism. So I'll show you kind of some of the challenges of doing scaling based on latency. So this is our SLO. And I'll show you our model-based approach for dealing with this stringent SLO specified in the upper percentile of latency. And also how we use fine-grained workload monitoring to make the data movement easier and faster when you're doing the scaling up and the scaling down. And I'll show you some experiments we did a while ago, but also what you're seeing during the demo is this being actually done on the SCADS nodes. So in order to do this dynamic scaling in the storage tier, we actually designed a storage system that we could use to do the scaling. It's called SCADS. And it's a key value store. And if we look at kind of the SCADS stack, so starting at the bottom, we have Mesos. And Mateo will be talking more about what Mesos actually is. But from our perspective, it's kind of like the cluster manager that gives us our resources when we need it. So this we'd ask Mesos for more servers or release back to Mesos servers that we no longer need. And each SCADS server node is running a local copy of BDB. So this is how we actually store the data. And then on top of that, we have this message passing layer, which is using Avro. So we kind of have these messages that both the clients use to talk to the database, as well as for message patching between the server nodes when they want to exchange data. And it's all in this Avro serialization format, which is really easy, kind of have the schema of the messages built in. And so Chris already explained to you kind of like the pickle part of the stack. And the other part of SCADS is that you can have different types of protocols for doing, say, a quorum. You could have range routing, so range partitioning. You could do hash partitioning. So in the context of this talk, we'll be doing range partitions on SCADS, but you can do a number of other things. And the director, the orange block, is what I'm talking about also today, the thing that's actually doing the movement between the storage nodes and scaling up and scaling down. So it seems natural to kind of use a classical closed loop for doing this elastic scaling in the cloud. So if you kind of build our loop together, we have some sort of controller that's going to make periodic decisions about what to make changes to our cluster. And then we have a SCADS cluster of however many nodes it is. So So we'll schedule some actions that will either move the data around, add servers, remove servers, whatever these actions might be. And the input to that would be, say, the upper percentile latency. Because remember, SLO is the upper percentile latency, so obviously that's the thing we want to control for. However, so there'll be some problems, actually, with trying this approach. So if we look at an example, so we have these storage nodes in the cloud, and we're looking at the server on the left. And we'll be looking at observations of its latency over time. And so here we say our threshold is whatever it is, the red line, and we're looking at the 99th percentile latency. So we get our first observation, everything looks great. We get our second observation, it's actually above the threshold. So the controller says, uh-oh, I need to move some data from my overloaded node. And it does that, okay, it relaxes. Then we get our next observation, and it's below the threshold. So the controller says, okay, let me just move that back. So as it turns out, this node is not overloaded. It's just that the signal is very noisy. So when you draw several observations from the 99th percentile latency, this is a noisy signal to look at. So one approach to dealing with noisy signals is just to smooth it over time. So let's try that approach. So here we have the same set of nodes, and we're looking again at the node at the left. And we have a couple observations of the 99th percentile, and I'll use the green line to represent the smooth version of those observations. So right now our server's doing fine. However, we get the raw observation is actually above the threshold, but our smooth observation, which we're smoothing over a long period of time, is still below that threshold. And then actually, our server now is getting overloaded, but the smooth one actually won't notice until much later. So we're smoothing over too long a period of time. So we kind of have this double-edged sword. So if you don't smooth or you smooth too little, your controller will have too many oscillations and may make incorrect decisions. If you smooth too much, you won't actually notice a real spike that's actually occurring. So if you look at some real data, so this is SCADS running on EC2, and we're just going to see what is the variance between observations of the 99th percentile, and we're just going to do over longer and longer smoothing intervals. So here we see the raw data of both the 99th percentile and the raw mean observation. And obviously you can see that the variance of the 99th percentile is much higher. And naturally, if we smooth both over time, they both have lower variance, but the 99th percentile is still so much higher than the mean. And if actually we want to get the same variance in the 99th versus the mean, we have to smooth for about 11 times longer. So this just shows you why the upper percentile is actually much more difficult to work with. So we've seen that the 99th percentile is kind of a noisy signal. So what we'd really want to do is have some other signal we can use that can kind of give us information about what the latency would be, but it's not as noisy. So this is why we use model-predictive control. And so what we can use instead of the noisy signal is use the per server workload as an indicator and a predictor of what the upper percentile latency would be. And so pretty much we need this model that maps a workload to an actual SLO violation. And we don't actually care what the latency actually is. We just want to know, would there be a violation or not? And so the way model predictive control works, just briefly, it has some model of the system and the current state of the system, and it determines some sequence of actions it should take to change the state of the system to some other state, and then it executes the first steps in that sequence of actions, and then reevaluates the state and continues. So if we look at our loop that we had before, we can actually now swap out the upper percentile latency and instead look at an observation of the workload. And now the controller will be consulting some performance model of the system in order to make the decisions about moving data around. So instead of using an analytical model, we actually build a performance model by benchmarking SCADS on EC2. And just to give you a flavor of how we did this, one of our models is called the steady state model, and it just represents the capacity of a single server. And so the way we build this model is by exploring the space of possible workload. And so the SCADS primitive operations are get and put requests. We build a model, we benchmark the SCADS under different ratios of get and put requests, as well as different volumes of workload. And so it's what we have here. So we have gets on the X and puts on the Y. And so we benchmark for different ratios, like 50-50 and 80-20. And we get, so the green represents when the workload is not high enough to cause an SLO violation, and the red dots represent when there was an actual violation. So using that benchmark data, we build this binary classifier that divides this space. And so now we know that the workload that is below this binary classifier is no violation, so it's safe workload. And then workload above this line would be a violation. So now we have our performance model and our augmented control loop we're going to react to workload instead of latency. Let's see how that would work in our toy example. So again, we're looking at the server on the left, and we're going to look at workload over time and view observations. This workload is requests per second. So a few observations so far. Everything's looking OK. Then the workload gets higher and higher. OK, now our server's overloaded. The controller sees this and moves half the data away. But the problem is our server is still overloaded. And we could continue splitting in half again, but that might take too long, and we want to actually isolate our performance problem faster than that. So it would be nicer to know which data should I move away, how much data is necessary. And so what we really need is a kind of more fine-grained workload monitoring than information about per server workload. So particularly since we're looking at the upper percentile latency as our SLO, data movement often impacts performance. This is especially noticeable looking at the tail of the latency distribution. So what we'd much rather instead is if we had more information about workload, more fine-grained than per server, we could decide which data to move away to only alleviate our performance problems. And so we could be able to move the data quicker and solve the problems more quickly. And in addition, we can actually scale down faster, because if we only moved away enough data to solve a performance problem, then later on when we want to scale down, it's easier to move less data back, and then we can coalesce our servers. So the way to accomplish this, we just want to monitor the workload in a finer granularity than per server. So we actually have small data ranges in which we monitor the workload, and these data ranges I'm calling bins also represent the data, the unit of granularity for moving data amongst the servers. So to summarize kind of our approach, we're going to use this fine-grained workload monitoring and our performance model, and it helps our controller in a couple of ways. For example, if a server is overloaded, we can determine how much data should we move away to solve the performance problem. Also on the flip side, if a server is underloaded, we can kind of say how much extra room does it have, so we want to kind of keep our servers as tightly packed with workload as possible. In addition, we actually know when it's safe to coalesce servers, because remember, we're interested in scaling down. So if you're only looking at latency and two servers have latency that's OK, you don't really know whether it's safe to kind of move all the data from one to the other, and kind of the workload monitoring performance model helps you make that decision. In addition, we also use replication for predictability. So if you're running in the cloud and there is a lot of variability, one technique for for smoothing that variability is to use replication. So I'm just going to walk you through kind of how the controller works. So it makes periodic decisions, say every 20 seconds is what we used. And it operates in 3 stages. So it has a replication stage in which it looks at, is there any server that has a data bin, so a range of data that's small enough, and this is a parameter, small enough that you can no longer split it, so you actually want to start replicating. The second stage is when you want to start partitioning. So if there are multiple bins, say on an overloaded server, you can choose amongst which bins to move away. So it would be partitioning. And the third stage would be allocating more servers. So if you have a number of hot standbys, since it takes time to actually boot up servers, you might want to have a number of hot standbys. This is when you would allocate servers. Or if you're coalescing, you can remove extra servers. So I'm actually showing this diagram here. It represents kind of information about 7 nodes in this hypothetical system. So each vertical part represents information about one server. So the bottom and the blue is kind of the bins on each server. And in the yellow above the line is the workload on each server. And then we have our threshold in red. So our first stage, we replicate, and we see, OK, node 1 is overloaded, and it only has 1 bin. So we're going to go ahead and replicate that to one of our hot standbys. And so we replicate it to node 6. And we've now alleviated the performance problem on that node. So now it's at our partitioning stage, and we address, what's our other overloaded server, node 2. And we consult our performance model, and it tells us, these are the bins that we should move away in order to make the server no longer be overloaded. It also helps us figure out which is the best destination. And again, we want to kind of use this greedy best fit approach, and we keep the bins as densely packed with workload without being overloaded in order to make it easier for kind of scaling down and removing extra servers later. So here we're picking node 4 because it's the most loaded, underloaded server that can accept the extra workload. So we'll go ahead and make that move. OK, so now all of our servers are under our threshold, so we're satisfied. We used one of our hot standbys before, and so if we had set that we wanted to always have 2, we would go ahead and allocate another server. So that's kind of like the scaling up part of it, and scaling down is analogous, kind of remove extra replicas, coalesce data, and remove extra servers. So I'm going to show you a couple experiments we ran before for our FAST paper, and now obviously you're watching the experiments that are running now as well. So in these experiments, we had 20 SCADS servers on EC2. These were small instances. We were running 800 megabytes of data, because SCADS keeps everything in memory for performance considerations. and we were operating with 100 millisecond slow on read latency. So there's two experiments I want to show you. So one is a hotspot workload. It's about an hour long, and there's slight variations in aggregate workload. However, there's an 100% increase that occurs in 5 minutes, but all that extra workload is directed towards a single data item. So this will kind of exercise our ability to replicate quickly and react to a hotspot. And it's actually based on a spike that was experienced by CNN.com during the 9/11 attacks. So the second profile is the diurnal pattern, which just represents scaling up during the day and scaling down at night. And this is actually based on a trace from ebates.com. And so we use a Zipf data access distribution, but the workload volume is from ebates.com. And so the actual workload is 24 hours long, and we just replayed in 2 hours to see the results faster. So if we look first at the hotspot workload, so I'm showing here actually the aggregate workload over time. And so you see it's kind of bouncy, but more or less straight. But after about 10 minutes, it's a slight increase in aggregate workload. However, we look at the same workload, but per bin. So we have these 200 bins across the servers. And all of the extra workload is directed at one data range, so one bin. And all the other 199 are so low in comparison that they're all kind of line up along the bottom. So this is the workload we're dealing with. So I'm going to keep the per bin workload as reference, because these will all be over time, the same time frame. So if we look at our performance during this time, this is the 99th percentile latency, and the red represents our threshold of 100 milliseconds. So you can see that there's obviously a spike in performance when the event actually hit, but we were able to recover it from it fairly quickly and maintain our performance over time. And then finally, we can see the number of servers we have over time. So we started from about 10, and I think we went to about 18. And all these extra nodes were actually replicas of this hot data item. So we added them over time to able to handle this 100% increase in workload that was all directed towards a single item. So the next one was the diurnal workload, in which we show scaling up and scaling down. And so the top graph shows you the aggregate request rate over time. And so obviously it goes up, and then it goes down as it goes into the evening. And so we actually ran two experiments to kind of compare what will be the effect of over-provisioning your cluster versus the ideal case. So the ideal case shows how many servers would you have used to support this workload if moving data was instantaneous and free and just happened automatically, taking 0 time. And so that's the light green, this light green along the bottom. And then the other two experiments we did was we over-provisioned our system by either 10% or 30%. And this just represents the workload that's input into the controller. We kind of amplify it by either 10% or 30%, and then see if we ran our dynamic controller, how many servers did it actually use. And so that represents the 2 lines above the ideal. So as you can see, we kind of hung the ideal line, but slightly shifted up because we are using a little bit of over-provisioning. And finally, if you look at what our savings were, so we can compare the savings to the static allocation. So if you had the number of servers at the very beginning of the experiment, that would have satisfied the highest part, the highest workload amount. So if you knew exactly what the peak was going to be and utilize your servers 100%, in our case, you save about 16%. However, no one actually uses their servers at 100% capacity, so you'd over-provision a little bit in that regard. So compared to someone using a static allocation but over-provisioning by 30%, you actually save 41% in our case in the dynamic version. So there is this cost-risk trade-off as far as over-provisioning. So like I mentioned, you can amplify the workload, make it seem higher than it is, and this gives the controller more time to actually move data around and kind of give it some slack time for making decisions. But it is going to cost you more because you are actually using more servers. And so we kind of compare what was the over-provisioning, how the over-provisioning factor affected the results of our experiments. So if we look at the diurnal results as far as SLO, and remember our SLO is made up of a couple of parameters. There's like the threshold, so in our case it was 100 milliseconds, the percentile, so 99th percentile, and the interval over which it's evaluated. So you can have, say, 1 minute, 5 minutes, 20 seconds, that type of thing. So in the table you see for different intervals and also for different over-provisioning factors, 30% versus 10%, what was the maximum percentile that we actually could have achieved during that experiment? And you can see, obviously, that when you over-provision more, you can get a higher SLO guaranteed, but it is costing more. So, but if you over-provision less, you still get a pretty good guarantee. So even 90th percentile for a 20-second interval, which is pretty good at 10%, but this is kind of the trade-off that you have to think about. So to conclude, we know that elasticity is great, and we can use it for storage servers. But when you're looking at an SLO that's really noisy, you have to kind of use a different signal for dealing with that. And so we showed you our model-based approach for building a control framework to do that elasticity for storage servers, and also how fine-grained workload monitoring helps us in scaling up and scaling down and making those decisions about which data to move and where to move it to. And I showed you some experiments on EC2 for the hotspot and diurnal case, and also we are running the demo currently, so you can see those experiments as well. Thank you.
Thanks, Beth. This is very interesting work.
Okay.
I wonder whether you can comment on the noisy piece. I mean, you remarked a few times about that. I wonder how much of that is the effect of intrinsic delays. I mean, because moving workload from one server to another takes some time. It also, measuring the effects takes time. And we may be facing a classical problem, which is a system with delays. I mean, the most classical example of that is the drunken driver. I mean, the problem with that is that by the time the signals reach his mind, I mean, it's too late, right?
Mm-hmm. So I think there's a couple problems that we address here. I mean, I think even when we're not moving data, we did observe that the 90th percentile was noisy, so that's part of it as well. But I think another thing that complicates the control is that when you're moving data, it's hard to use a typical control because the effect of moving data is not readily visible. So you can move data and you don't know the effects. It's not exactly correlated with what happens afterwards.
No, that's exactly my point, yes. I mean, it's not a linear controller, and it's not a controller without delays. I mean, the delays are an integral piece of it. I mean, we can talk more about that.
Right.
Thank you.
So thanks for a nice talk. Your approach is primarily a sort of reactive one. So when the servers are overloaded and you start looking around to, where you can pick out pieces and move them somewhere else. I'm wondering to what extent can you use a similar approach in a preventative style? So if you can characterize workloads ahead of time, can you be more clever about where you place them so you avoid overloading the servers to begin with? Mm-hmm. I mean, have you thought at all about whether you can use these same ideas for preventing overload?
So we kind of approached using the idea of having a historical workload. So for instance, you have a diurnal pattern, and it's kind of the same thing every day. You could use a historical workload to kind of ramp up beforehand. But we kind of felt it was more interesting to kind of approach the unexpected workload changes that you may not necessarily be able to kind of prevent because you don't expect them at all to happen. But I think ideally you could use both at the same time.
Hi, Beth. Two questions. The first one, could you give us a little intuition behind the noisy latency data versus the apparently not so noisy workload data? Is it a function of that you can sample the workload more often and therefore you have more data points to effectively do smoothing over? Or is there some amplification effect because of queuing or something like that inside the system? Or is it both? Or something else that I haven't thought of?
So I think it's a combination of factors. One, that the workload for us is in generally less volatile than the 90th percentile. And I think it's also influenced by SCADS being a more or less simple system, and that the requests are sort of independent. So you have these simple, get requests, put requests, and they kind of linearly add up. So that's why workload kind of is a good metric to use in our case. So in other systems, this may not be true, and so you'd still want to maybe use a model-predictive approach, but maybe use a different set of underlying features that you're looking at. But in our case, because SCADS is kind of a simple key value store, and also because we observe the workload is less volatile, that's why we chose it.
Okay, we could take that bit offline. I would actually argue that answer suggests the opposite answer, but never mind. Question number two, which is what I'm more interested in, is can you talk a little bit about sort of the throwing control theory at this? What does it tell you about things like stability and ability to reach the good operating point quickly?
Okay, that might be more of a Peter question. But I don't know if Peter wants to address it, but I think based on, there's feedback control. So I think from what Peter's explained to me, so that in a feedback control loop, you're kind of trying to optimize for one variable, and you don't want to oscillate around it. But so I think Peter does want to say something.
I think the main difference between the reactive, the classical control loop where you're reacting to latency is that you don't really know what the right number of servers is. You just, you see high latency, so you add more servers. You see low latency, you remove servers. But because we're looking at workload and we trust our performance model, right? The assumption is that the performance model is correct. If the model is wrong, then all bets are off, right? But if it is correct, then for a stable workload, we can give you the exact right number of servers and the right allocation. So there is no, you're not converging to anything. You can like immediately give the right number. It might take a while to boot up the machines, but it doesn't have the issue of the reactive controller where you are kind of going up and down and you're oscillating. So that's, I think, the advantage of the model-based approach where, even when the input signal is stable, you can give the right answer right away.
Okay. Swallow hard and get rid of that if at the beginning of the sentence and it's fine.
Right.
Yeah.
Okay, I think we have time for one more question. While we're doing that, Matej can probably get set up.
Yeah, very interesting work, Beth. So seemed to me that the key is really to actually be able to characterize and model the workload. Have you thought about try to think about workload actually comprised of a couple of those components? For the diurnal patterns, right? You have some patterns which seem to be quite stable and it does not vary from day to day. And then there's some spikes that may be actually transient. And I wonder if you can actually take a multi-scale approach and try to build models that way. Because there are components that's kind of invariant, which you can actually predict quite well. You can actually provision it very well. And there's a parts that you cannot really predict in some fine precision where you can actually try to do something, to model that. So have you thought about those, try to separate the workload into multiple components and try to treat them in a different way?
So we didn't actually try modeling them separately, but we kind of used the notion of different types of over-provisioning. So over-provisioning, like amplifying the percentage of workload works well for, say, a more diurnal pattern where like all the servers are increasing in workload and they're all decreasing kind of together, whereas having extra hot standbys works better for, say, a hot data item that you need to replicate quickly. So that's kind of how we deal with both of those at the same time, but we didn't explicitly model them separately.
Okay, let's thank Beth.